Okay, Bismillahirrahmanirrahim. So, welcome to this very important lecture on primarily Markov chain, Monte Carlo, or Monte Carlo Markov chain. I don't know kiska correct sequence kya hai, but it means just these two things together. So, in the last lecture, we have gone through the details of this Bayesian formula. So you need to keep this in mind that the machine learning algorithms are not capable of measuring the uncertainty in the predictions. On the contrary, the Bayesian approaches can give you an idea about the uncertainty. But the condition is that you are supposed to have knowledge of two things, which is the likelihood function and the prior function. So we will see in the hands-on today how these functions can be estimated, but it's primarily based on the user's own knowledge. So the prior function and the likelihood function are primarily PDFs. So just keep that in mind. So that makes it simple because we already know many PDFs, and if we know that some particular prior, for example, some call center data follows the, let's say, the beta distribution. So we can have a prior which reflects the beta distribution. तो हम prior अपना खुद बना सकते हैं, ठीक है? In a particular range, obviously, based on our own knowledge. इसी तरह से we can also estimate the likelihood function, and based on that we can estimate the posterior probability. So the whole thing about the Bayesian is कि जो चीज आप लोगों के समझने की है कि this evidence is not easy to compute. So if you write down the formula here, so probability of B equals to integration over probability of B given A multiplied by probability of A dA. So अब इसका that means कि A is the set of all the model parameters. ठीक है कि क्योंकि अगर मैंने B निकालना है तो मुझे तमाम A पे इंटीग्रेट करना पड़ेगा, और तमाम A क्या चीज़ है? A is the model जो कि हम लर्न करना चाह रहे हैं. So it is not possible for me to calculate this integral very easily because I have absolutely no idea about all the possible values of A. There could be so many models, right? How can I integrate over all the possible values of A? Therefore, calculating this evidence becomes a headache. It is almost impossible. So, लिहाजा हम ये काम करते हैं कि we are estimating the posterior through sampling. ठीक है, तो मैंने आपको लास्ट टाइम जहां पे हमने लेक्चर खत्म किया था, I told you कि the Bayesian approach is concerned with estimating the posterior distribution, which is the distribution of interest in machine learning, based on the likelihood and the prior. So you specify the likelihood function, you specify the prior function along with their parameters, and based on those values, I have 2 or 3 algorithms जिसकी base के ऊपर I can estimate the prior through sampling. So in this case, you can say I have the prior, I have the likelihood, and based on sampling these two distributions, I can estimate the distributions of the posterior. सही है? So posterior is what I want, posterior is what I'm interested in, and that is the whole game. And when I sample the posterior like this, then it becomes possible for me to measure the uncertainty, which is not actually possible in machine learning. So machine learning can give you the predictions, but it has nothing to do with uncertainty. On the contrary, the Bayesian approach is concerned with beliefs. जैसे हमने last time बड़ी तफसील में देखा था. So it is due to this concept of beliefs that I'm able to measure the uncertainty in my predictions. Okay, so that is the game that you need to remember in Bayesian learning. ठीक है? So अब obviously अब इसमें automatically you will now ask me कि सर ठीक है, मेरे पास कॉल सेंटर का डेटा है, मेरे पास बैंक्स का डेटा है, ऑनलाइन बैंकिंग का डेटा है, I got data about, let's say, telecom transactions. So I have to predict, for example, the duration of a call, right? So I can tell you the likelihood function. If you don't know the likelihood function, then you can assume a likelihood function. And if does not fit it, then you can take another likelihood function, because I told you that both of these are PDFs, और PDF functions हमारे पास approximately 10 standard PDF functions हैं, उनमें से कोई ना कोई तो ये दोनों follow करते होंगे. So primarily ये वो normal function ही होता है जो follow होता है. Primarily it is the normal distribution, but it could be the Poisson, it could be the beta distribution, it could be the uniform distribution for that matter. So there is something जिस पे आपको थोड़ा सा experience लगाना पड़ेगा, ठीक है? But the point is that for the MCMC methods, I am always able to specify the likelihood and the prior functions based on their PDFs. And when I have done that, then it is all up to the algorithm to give you the posterior value through MCMC sampling. Okay? So that is the whole game. So अब आप मुझसे obviously पूछेंगे कि how does this sampling work, right? I mean, what happens actually? तो उसके लिए, first of all, in the last lecture, we saw quite this in detail, the Monte Carlo method. So I told you that the Monte Carlo method, basically you use random sampling to obtain the results. ठीक है? तो इसको हम कहते हैं, you need to keep this in mind, that this is actually called a point based sampling. ठीक है? So given a space of options, or given a safe space option, I sample a single point. तो जैसे मैंने किसी चीज की I have to estimate the expected value of a random variable which takes a value between, let's say, 20 and 200. सही है? तो what I will do a Monte Carlo. Monte Carlo में करूंगा कि I will sample a set of values at time step 0 and I will take the average. Finish. Then I will sample it again and I will take the average. Then I will sample again a set of values, take the average. I will repeat this for thousands of steps. ठीक है? And when I take the average of all the averages, that converges to the expected value. That's how it happens. So through sampling, I am actually able to acquire something which is very, very concrete. Although I don't have the actual data, I just have the sample data. But based on the sampling, I'm able to basically get what I want. So that is Monte Carlo. So the point is that if I am, agar मैं sampling, what gives here? If I am sampling over this time stamp, so I have these time stamps, okay? So each sample that I'm doing in a Monte Carlo, so I sample here, I sample over. So all of these samples are actually independent of each other. So none of these samples are dependent. There is no correlation between the samples. There might be a correlation, but in the case of Monte Carlo, we are not considering any correlation. So you need to keep this in mind. Okay, these samples are actually extremely independent from each other. There is no correlation between the Monte Carlo samples. So in this way you can, because देखें आप correlation पे compromise करेंगे तो आपकी analytical capability कम होगी. लिहाजा हम Monte Carlo में we can't achieve much. We can achieve, ठीक है, आप expected value calculate कर लें, calculate the variance, calculate the standard deviation, calculate the some other related parameter to these mean and variances, etc., etc. But you can't do much in Monte Carlo. ठीक है? So still it is a very famous technique. So we saw some examples here. ये मैंने आपको शायद उसका hands on भी करके दिखाया था कि the difference between a simulation and a Monte Carlo. So you can see कि Monte Carlo में in each timestamp you are sampling a large number of coins from a box and observe the probability of heads and tails. And over all these iterations, then you average and then you get the what you want. So the probability of getting the head. So in the simulation, so what you're doing is you have a pseudo random number, although in the case of Monte Carlo, we are completely random. So yeah, it's completely randomized. In the case of a simulation, it is a pseudo random number, which you sample from a uniform distribution and you consider that as a coin toss. So the concept of simulation involves a pseudo random number and just one number at each time step, while the concept of Monte Carlo involves a large number of values at each timestamp, and it's not pseudo random. On the contrary, it is completely random. Okay, and that is why it is very strange. So I can combine these two methods to have a Monte Carlo simulation. So typically you will hear this word of Monte Carlo Smith. So at each go, I will have a number. So at each timestamp, I will sample a large number of coins, let's say from a uniform distribution, and then make a decision with respect to this. So I will sample them randomly, and I will sample a large number of coins, and the rest I will do the same as it is written in the simulation. Okay? So that combines the two approaches. So then we saw that these are the applications. So these are some of the variables that you can estimate. और फिर हमने hands on के through ये करके देखा था कि we have these 3 parameters to cater for in Monte Carlo. So if you have generated the samples from Monte Carlo, then we have to ensure that the sampled mean is close to the true mean. And I showed you that in the last hands-on. Okay, that does happen. So that is to check the biasness, and then you can also check the consistency. So if you are actually converging to the true parameter values given a large number of samples, then the algorithm is said to be consistent. And we can have multiple estimators, but the one with the lowest variance is called efficient. So lowest variance is कि जिसमें आपका जो histogram है वो बहुत packed है, वो बहुत packed है mean के इर्द गिर्द, that is the lowest variance. So it turns out कि अगर आप Monte Carlo के through you do the sampling, then it turns out to be not biased. There's not much difference between the actual mean and the sampled mean. It turns out to be consistent कि you always converge on the true value of the parameter. That's a strange ये एक strange result है, but that always happens. Even in Markov chain Monte Carlo, ये guarantee आपको मिलती है कि it is definitely going to converge to the true value of the parameter. Therefore, the Bayesian methods can act as the substitute for the machine learning approach, because there is a statistical guarantee कि आप model के parameters जो exactly required हैं आप उस पे converge कर जाओगे. That's the guarantee that is given by MC and the MC method. ठीक है? So इस चीज का आप लोग ख्याल रखें. बहरहाल और variance में ये कि if देखें अगर if it is not biased and if it is consistent, then it is expected to have the least variance. तो ये तीनों concepts एक दूसरे के साथ मिले हुए हैं. ठीक है? तो for more details, please look at the hands-on. So then we sorry about that. Yeah. So then we saw this very good example of the Excel file. I showed you all the examples in which we were just doing the Monte Carlo. So whenever we press the F9, so it was doing a Monte Carlo over 500 or I don't know 5,000 rows. I forgot कि कितने थे. और वो मैंने आपको सारा करके बता दिया था कि किस तरीके से वो होता है. So this is the histogram of the Monte Carlo simulation results. So you can see कि it is approximating the normal distribution, although it is a multimodal distribution. ये मतलब इसकी peaks ज़्यादा हैं, तो this is not exactly normal, but we can make it better. We can always make it better if we increase the number of samples, and we increase the number of samples. उससे आप बेहतर बना सकते हैं, या फिर you can use some other method like the MC method, जो कि आज हम पढ़ेंगे इंशाल्लाह. ठीक है? So ये तो खैर converge कर गया था, I think it did converge. So this is a very good example जो कि आप लोगों को देखनी चाहिए, and maybe some of your projects will simulate the same thing. So it's a big deal कि I am able to say a lot of things about my profit, not by using machine learning models, but just by using basic Monte Carlo, जो कि बहुत simple चीज है. ठीक है? So उसके बाद शर्त ये है कि आपको ये पता हो, like here we specified the you need to know the min and max. तो वो आपको business knowledge से पता चल जाएगी. For example, if you are working with telecom data, anyone can tell you the min and max of a given variable. कि minimum इतना होगा, max इतना होगा. You will get to know through the sample that you have कि यार ये तो normal distribution follow करता है. So let's do it. So just give it the range, sample from the normal distribution, put that in the formula, ditto for the other variables, and get out the profit or whatever. तो ये काम आप टेलीकॉम डेटा में भी कर सकते हैं, फाइनेंशियल डेटा में भी कर सकते हैं. You can do anything you want without doing any machine learning. Okay, so that's what we want to experiment in the projects in this course. But also we also saw that we can plot the cumulative distribution plot, etc. etc. That's good. So this is these are some of the applications. So we will, I'm not getting the time to design the project, frankly मैं इतना busy हूँ. कल हम लोग वहाँ तब्बा हार्ट में गए हुए थे, so we had a presentation there. It was very useful, very beneficial. Today आज मुझे फास्ट जाना था, आज PhD proposal defense था, फिर ये आपके लेक्चर की मैं तैयारी कर रहा हूँ 2 दिन से. So मुझे प्रोजेक्ट्स का टाइम नहीं मिल रहा, लेकिन it will be done very soon इंशाल्लाह. तो the data will be like this. ठीक है, हमें बेसिकली मशीन लर्निंग से कंपैरिजन करके दिखाना है. बहरहाल ये हमने एग्जांपल देखी थी कि ये सेल्स में क्या किस तरह से होता है, तो व्हाट दे रिपोर्ट इज डिफरेंट फ्रॉम द रिजल्ट्स ऑफ द मोंटे कार्लो सिमुलेशन. ठीक है, सो यू विल आल्सो फाइंड दिस. तो ये कुछ उसके वो थे. अब हम आते हैं असल काम के ऊपर. ठीक है, अभी तक जो हमने पढ़ा है, यू हैव टू पे अटेंशन टू व्हाट आई एम सेइंग, ताकि आपको सही तरह चीजें समझ में आ जाएं. What we have read up to now is the Monte Carlo approach, right? We know what it does. It's a point estimate. It is used to estimate the parameters of a distribution, but primarily we're looking for things like expected value, variance, etc., etc. ठीक है? If you want to estimate the posterior based on the concept of based on the likelihood function and the prior function, then you have to use the class of methods which is called MCMC. ठीक है, तो last time I'll just go through this slide for a recap. Last slide, in the last lecture I told you all these things already, so I taught you this, but I'll just do a revision here. Okay, the posterior is my prediction. If I am able to estimate the posterior distribution of my variable of interest, that means that I am able to predict that variable. Okay, like we do in naive Bayes. Okay, so I can estimate the posterior based on the likelihood and based on the prior. So they are proportional to each other, and the posterior is approximately equal to these. That's my assumption in the whole Bayesian scenario. This मैंने आपको ये बताया था कि this thing is simple if the likelihood and the posterior follow the Gaussian distribution. जैसे हमने भी देखा था कि this could be the likelihood, sorry about that. So this could be the prior, and this could be a very good likelihood, and the posterior could be approximated somewhere here. So we are using sampling process to estimate the posterior. That is the most important thing that you need to keep in mind. Okay, I am not using some formula. I am just sampling values from likelihood and the prior. So collectively मुझे बताया गया है कि likelihood function फलान distribution को follow करता है. The likelihood function follows a particular distribution in a given range. Ditto for the prior. Now please calculate the posterior. So I am able to do that by using the MCMC algorithms. ठीक है? So one of the algorithms is called Gibbs sampling, and the other algorithm is called Metropolis Hastings. So Gibbs sampling has some limitations. Metropolis Hastings is the more commonly used algorithm, which has some extensions, जो कि आपकी hands on में इस्तेमाल अभी Stan library में जो हो रहे हैं. It has some extensions. ठीक है? तो but we first have to understand कि MCMC, how does it work? So system, अब देखिए ना यहाँ पे word क्या add हुआ? Systematic random sampling. And in the case of Monte Carlo, I was not using the term systematic. I was only using the term pure random sampling or complete random sampling, not pseudo random sampling. But what do you mean by systematic? That is what we want to discover. Okay. दूसरा जो problem आपको समझना है कि we use these algorithms when we have a high dimensional data. We are not concerned only about one variable. We are dealing with the typical training data scenario, जिसके अंदर आपके पास multiple columns हैं. Each column follows its own distribution. Most of them will be Gaussian, but they have their own distribution. So it's a multivariate Gaussian. ठीक है, मैंने आपको ये कॉन्सेप्ट पढ़ा दिया और मल्टीवेरिएट गॉसियन का. ठीक है, ऑल्दो मैंने उसका आपको बहुत तफसील नहीं बताई, उसकी लैब अभी बाकी है, लेकिन यू गेट द कॉन्सेप्ट राइट के आई हैव रैंडम वेरिएबल ऑन डिफरेंट एक्सीज and all of them collectively form the Gaussian distribution. So it is extremely difficult for me to sample directly from a multivariate Gaussian distribution. It's not possible for me कि मैं directly एक multivariate Gaussian distribution से sample करके अपना कोई result निकाल सकूं. ठीक है, तो MCMC method जो है ना, they allow me to estimate the posterior. They allow me to estimate the posterior distribution of a given machine learning problem based on the likelihood and the prior function of the multivariate Gaussian. सही है? तो ये जो prior और likelihood है, they are concerned with this multivariate Gaussian distribution. और इसका जब हम एग्जाम्पल लेंगे तो आपको पता चल जाएगा गिब्ब सैम्पलिंग किस तरह काम करता है, मेट्रोपोलिस हेस्टिंग किस तरह काम करता है. मेन इशू इज के यू नीड MCMC when you have a very high dimensional data or a high dimensional data for that matter consisting of 10 columns or 13 columns in the feature space, and you want to estimate the posterior because of the fact that you don't have the evidence with you. So that is the main scenario जिसको आपको याद रखना है, जो कि आपको MCMC methods इस्तेमाल करने का जो आपको फाउंडेशन देगा. ठीक है. So now I told you that we are doing systematic. What was happening in Monte Carlo? I had these timestamps, and I told you in the previously in today's lecture, I am sampling independently at each timestamp a set of numbers through complete random sampling. ठीक है. So I assume there is no correlation between these samples. I might be wrong. So MCMC goes one step ahead and says that this sampling process should be systematic. इसका मतलब क्या है? इसका मतलब ये है कि the next sample, ध्यान रखिएगा, the next sample is generated based on the information of the previous sample. ठीक है, I'll just write that down. Just this is again, this is a recap that I'm doing. The next sample is generated based on the value sampled from the previous timestamp. That is the main game जो कि हमें खेलनी है. ठीक है. So अब आप कहेंगे अच्छा यार जी.
Sir, it's only for n-1, only last या previous सारों को consider करके next का.
That's a very good question. In fact, it's only the previous value because that's what happens in the Markov chain. Markov chain is a data structure which has been named after the Russian mathematician Andrei Markov. और उसका hypothesis ये था कि whatever happens at the current timestamp is dependent only on the information at the previous timestamp. So your current situation depends only on the situation at the previous timestamp, not the one before that. So we are just depending on information which is 1t-1. That is it. So now imagine what happens with respect to a sampling scenario. Okay? Let me draw the axis here. Let me just assume that this is the x-axis and the y-axis. If you have two variables in the multivariate Gaussian distribution, so I sample, let's say, first in the y direction, and I keep the value of x fixed and I sample y. Then I keep the value of y fixed and I sample x. So this value that is generated based on this value. And then I can again fix the value of x and I sample y. So in this way, the search is going to proceed. Okay? It turns out that when you do this sampling systematically in this fashion, so you always converge to the true posterior distribution. That's a extremely strange result. आप कह रहे हैं कि कुदरत की तरफ से ये result है. किसी किस्म का कोई भी problem ले आए आप जिसके अंदर you got a multivariate probability distribution, you will be able to always estimate the posterior, and there is a statistical guarantee that you will always converge on the required parameters. तो आप posterior distribution जो है ना उसको approximate कर सकते हैं. That's an extremely strange. You can think of the most weird problem, and you will be able to get the posterior for that. ठीक है, मुझे time मिला तो मैं आपको एक problem का वो करके, क्योंकि मैं उस problem का मेरे पास R code है, but I don't have the Python code, so I will have to write that. So maybe next class में आपको दूंगा. आज हमें और बहुत कुछ करना है इंशाल्लाह. ठीक है. So is this thing clear? Is the concept clear? The difference between MC and MCMC is basically the introduction of the Markov chain. So what I'm doing is I am sampling with respect to the Markov chain, with respect to Monte Carlo, but the next sample is being generated based on the value at the previous timestamp, based on the sample that you generated the previous timestamp. So now अब आपको ये बात मुझसे करनी चाहिए कि नाउ थिंग्स गेट कॉम्प्लिकेटेड बिकॉज there is a correlation between samples. अब मामला खराब हो गया, ठीक है? Correlation between samples है तो now things get more complicated, the mathematics gets more complicated. But it turns out कि MCMC approach is the standard approach, not the MC approach. MC approach आप बच्चों वाली चीजों के लिए इस्तेमाल कर लें, जैसा कि मीन निकालना है, वेरिएंस निकालनी है. But the MCMC approach works in the normal case because in the normal case the training data that we have does follow the high dimensional probability distribution. सही है, जितना भी ट्रेनिंग डेटा आपके पास मशीन लर्निंग का आता है दैट इज मल्टी डायमेंशनल, सो इट फॉलोज द मल्टीवेरिएट गॉसियन. मोस्ट ट्रेनिंग डेटा फॉलोज द मल्टीवेरिएट गॉसियन डिस्ट्रीब्यूशन. वो हमने कभी उसको सेंस पे सोचा नहीं है ना. अगर हम उसको सेंस पे सोचेंगे तो वो बेजियन का जो पूरा मॉडल है वो उस पर फिट हो जाएगा आके. तो हमने अब करना यही है इस कोर्स में कि हमने बेजियन को ये कंपेयर करके देखना है कि मशीन लर्निंग के साथ इसका कितनी मैच आता है, क्या लिमिटेशंस हैं, क्या पॉजिटिव्स हैं, क्या नेगेटिव्स हैं. दैट्स व्हाट यू नीड टू अंडरस्टैंड. सो द बेजियन वर्ल्ड opens up a new door in which you can estimate the same predictions but by using the Bayesian methods of sampling, primarily MCMC. ठीक है, उसके अलावा भी हैं, वो फिर हम बाद में देखेंगे. अब फिर उसके बाद फिर we saw this example. ये तो खैर वो इसमें मैंने आपसे कहा था कि the Bayesian will tell you the belief. So we are pretty sure that the value of the parameter is quite near zero, and but we think that there's an equal likelihood. So we are talking about the beliefs here. ठीक है, तो in the Bayesian language you talk about beliefs or the uncertainty. ठीक है, and I discussed with you the likelihood function के likelihood function का मतलब क्या होता है. देखिए सिंपल सी बात है कि whenever you have to fit a model to a data, the model has some parameters. जो डेटा का सैंपल आपको दिया गया है, द ट्रेनिंग डेटा दैट यू आर गिवन हैज बीन सैंपल्ड एंड इज अ रिलायबल थिंग. सो यू वांट टू डिस्कवर व्हाट इज द लाइक्लीहुड, व्हाट इज द लाइक्लीहुड ऑफ माय मॉडल जनरेटिंग दिस डेटा. ठीक है, आई विल ये लिखा हुआ है यहाँ पे, बट आई विल राइट इट डाउन अगेन. फॉर एनी मशीन लर्निंग और डीप लर्निंग एप्लीकेशन, दैट इज द क्वेश्चन दैट यू वांट टू आंसर. What is the likelihood of my model generating this training data? So training data. So in this case, you obviously you have to define a likelihood function. अब देखिए ना, likelihood function is working based on the product of probabilities. The theta is the set of parameters that you want to estimate. X is the value that you have been given in the training data. So what is the probability that I can get the value of a particular column in the training data given a set of parameters? तो आप इसको estimate कैसे करते हो, ध्यान रखिएगा. You try out different parameters of the model that you want to fit, and the parameter which maximizes the product of the probabilities is the set of parameters that you want. ठीक है, so in order to fit any model to a training data, I can put thousands of parameter values for that particular model parameters. I have to try out the different values. ध्यान रखिएगा मैं क्या बात कर रहा हूँ. I have to try out the different values and find out the combination of values which is going to maximize the probability of seeing this data. अब इस approach में problem क्या है? इस problem ये है कि how many values should I try? A model parameter can take thousands of values, तो मैं thousands of values try करूंगा. तो we definitely need some algorithm which will help me estimate the likelihood function. We need some algorithm. ठीक है, so one of the algorithms that is going to help you achieve that is primarily the algorithms in the MCMC technology. So one of the algorithms that is going to maximize the likelihood function, which is called maximum likelihood estimation, is primarily Gibbs sampling. Gibbs sampling can help you maximize the likelihood. वो आपको बता देगा भाई ये वैल्यूज हैं जिसकी बेस के ऊपर आपका ये फंक्शन मैक्सिमाइज हो जाएगा. ठीक है, ये पैरामीटर की वैल्यूज हैं. सो दैट्स अ बिग डील कि थ्रू सैम्पलिंग आई एम एबल टू अप्रोक्सीमेट दिस. अच्छा, द सेम थिंग हैपेंस इन मशीन लर्निंग. मशीन लर्निंग में भी यही होता है. मशीन लर्निंग में भी वो जो मॉडल पैरामीटर रैंडम फॉरेस्ट का फिट करेगा, ठीक है, वो आपसे पैरामीटर वैल्यूज ले लेता है और आप जो पैरामीटर वैल्यूज देते हैं उस पे वो लाइक्लीहुड फंक्शन को मैक्सिमाइज करके दे देगा. लेकिन तरीका तो ये थोड़ी है भाई. लेट्स से कि मैंने कहा कि रैंडम फॉरेस्ट में 200 ट्रीज बना दें, ठीक है, बट मे बी 300 इज द आइडियल आंसर। आई डोंट नो कि 300 इज द, मैं तो चाहता हूँ कि एल्गोरिथम खुद ट्राई करे ना उसको, तो फिर मैं ग्रिड सर्च पे आ जाता हूँ। लेकिन ग्रिड सर्च जो है ना वो उसमें भी देखें, ग्रिड सर्च इज अ प्रीटी स्लो प्रोसेस एंड आई एम नॉट रियली श्योर कि जो वैल्यूज मैं ट्राई आउट कर रहा हूँ वो सही है भी कि नहीं। आई वांट द वैल्यूज टू बी सैम्पल्ड बेस्ड ऑन देयर प्रोबेबिलिस्टिक कंपोनेंट, दैट कैन बी ओनली डन थ्रू द सैम्पलिंग अप्रोच, जैसा कि बेसियन मेथड्स में हो रही है। अब मुझे नहीं पता कि वो जो आपका जो ग्रिड सर्च है which estimates the ideal values of the parameters, कि वो अंदर से either वो Bayesian sampling पे चलता है कि नहीं चलता, I really have no idea about that, but what I am saying is कि the Bayesian methods are more suited for the sampling methods than the machine learning models, ठीक है, so that's what we have to see, ठीक है, so that was the likelihood function जो कि हमें approximate करना है, और ये था this is the prior, this is the likelihood, and you know I can estimate this posterior based on that, ठीक है, so the posterior basically tells me कि actually वो कौन सी values हैं जो आपकी likelihood को maximize कर रही हैं, इसको हम statistics में कहते हैं map, maximum a posteriori, that is the maximum likelihood estimation के नहीं sorry, maximum a posteriori तो ये चीज है कि कौन सी वैल्यूज है मॉडल की जो कि पोस्टीरियर की हाईएस्ट वैल्यू आपको देती है, दैट्स द थिंग, ठीक है, तो व्हाट आर द वैल्यूज, व्हाट इज द हाईएस्ट प्रोबेबिलिटी दैट कैन बी अचीव्ड ऑन द पोस्टीरियर पीडीएफ, so in this case that is 0.1, that point is called the maximum a posteriori, ठीक है, इसको हम मैप कहते हैं, और बाकी अगर आपने पोस्टीरियर फंक्शन पूरा एस्टिमेट करना है तो आपको पता चल गया है कि वो हम एमसीएमसी मेथड्स के थ्रू कर सकते हैं, ठीक है, सो ये चीजें सारी पुरानी हैं, ये मैंने क्लियर कर दी थी आपको। प्रायर इज लेस श्योर क्योंकि दैट इज बेस्ड ऑन आवर ओन नॉलेज, likelihood is more sure because likelihood is estimated based on the training data sample that you have. You always have the training data with you, you always have the prior knowledge with you. If you want to use the MCMC method, then you have to make a function for likelihood, you have to make a function for the prior, give that to the algorithm and it will compute the posterior for you, ठीक है। हाँ, तो ये स्पेशली इन दिस, यहाँ पर तो एवरीथिंग इज वेरी सिंपल, बट वी सॉ इन द लास्ट क्लास के this is the situation where we definitely need the MCMC methods because we cannot assume things to be Gaussian. So if I have things in 3D, so let's say that this is 3D or 4D or whatever, so I have some Gaussian here, so this is pretty simple, but if I don't have the Gaussian, I have something like this, I have multi-Gaussian or some very strange shape going like this, but if this is the multivariate PDF, so in this case, if I want to learn the posterior, I definitely have to use MCMC, ठीक है। In the previous case, you might estimate this through some other methods as well, ठीक है, लेकिन अगर ये चीज है तो इसमें posterior को कैप्चर करना ज्यादा मुश्किल काम है, so it is not easy, so इस केस में you can use the Bayesian formula to basically estimate the posterior, but in this case it is not possible to do that, ठीक है, तो we definitely have to use the sampling method by moving like यहाँ गए फिर यहाँ गए फिर यहाँ गए फिर यहाँ गए फिर इधर गए फिर इधर गए, the next value depending on the previous one, in this way I am searching the whole space, तो इसके भी एग्जांपल अभी हम देख लेते हैं, ठीक है। I told you this Markov chain, this is like the standard automata, deterministic finite automata आप इसको कह लें, ठीक है, everything A to B में probability क्या है, so you can have this probability matrix, ABC here, ABC here, to A is 0 because there is no feedback loop from A to B is 0.1 and A to C is 0.9, and similarly for the other one. These are some other examples, so this is just to define you the concept of Markov chain, ये भी हमने discuss किया था, it's exactly like the Markov chain, so if I am slipping from this snake to here, so if I am in 19, so it depends only on my position at 62, तो 62 पे मैं पहुंचा तो मैं 19 पे आ गया, I don't care उससे पहले मैं 61 पे था या 51 पे था, nobody cares about that, ठीक है, so that's the thing, and this is one other example that we discussed, that when we want to go to any room, I want to go to the kids nursery so that will only depend on the situation कि अभी आप उसके parallel किस room के अंदर हैं. So I am in the living room, I can go here. I'm in the study, I can go here. I'm in the bedroom, I can go here. I'm in this small room and suite bathroom, I can go here. उसके अलावा absolutely not. सही है. So this is t minus 1. So at t minus 1, I could be in any of these rooms. And then at t, I will be in the nursery. So ये हमने ये बात देखी थी कि अगर मैं अपने घर में कमरों में जाने की प्रोबेबिलिटी निकालना चाहूं कि व्हाट इज द माय प्रोबेबिलिटी of being in the spare room, of being in the bathroom, of being in the kitchen or the garage or the games room for that matter. ठीक है, what is the probability? So that probability is going to be estimated based on आपके neighbors कौन से हैं. And if you repeat the MCMC method thousands of times, so eventually you will definitely converge on the probability of being in each room. आपको पता चल जाएगा अपनी जिंदगी को 1000 दफा या 10,000 दफा या 10 लाख दफा सिमुलेट करके कि मेरे घर की जिंदगी को सिमुलेट करके मैं आई विल कैलकुलेट द प्रोबेबिलिटी ऑफ बीइंग इन ईच रूम. वो मेरे सामने प्रोबेबिलिटी मुझे दैट इज माय पोस्टीरियर दैट आई वांट टू एस्टिमेट. वो मुझे मैं एस्टिमेट कर सकता हूँ. ये चीजें क्लियर हो रही हैं भाई?
जी सर.
हाँ, ये बहुत जरूरी है. ठीक है
सर.
जी.
सर जब मैं अंडरग्रेड में थी तो हमें एक चीज पढ़ाई थी, उसका मुझे उस वक्त ज्यादा नहीं समझ आया था, अभी समझ आ रहा है. वो ये था कि मार्कोव चेन्स, मॉन्टे कार्लो सिमुलेशंस यूज करके हम स्टॉक मार्केट फोरकास्टिंग भी करते हैं. तो वो ब्लैक शोल्स इक्वेशन एक होती थी, उसको यूज करके स्टॉक मार्केट की फोरकास्टिंग के लिए यूज करते हैं, राइट?
जी जी, देखिए मैंने आपको ये बात बताई है कि any problem in which you have to estimate some PDF, like मतलब prediction में भी तो यही होता है ना. The values that are predicted do follow a PDF. कोई भी values आप predict करेंगे, regression की values अगर हों, ठीक है, if they are numerical values, जैसे आपने stock prediction की बात की, तो that's a regression problem. A time series problem is also a regression problem. So I have to output the numbers. That's what I'm looking at. और ये मैं आपको बात बता दूं कि 70% of the problems in machine learning are solved by regression methods. In fact, regression is the actual machine. Classification जो है वो तो हमारी अपनी estimation होती है कि यार लोन देना है कि नहीं देना, गाड़ी बेचूं कि ना बेचूं, क्रिकेट खेलूं कि ना खेलूं, सही है, कल जाऊं कि ना जाऊं. तो ये तो हमारी अपनी एक अंडरस्टैंडिंग है, ठीक है. बट एक्चुअली machine learning deals with regression because you have to predict the actual numbers. That's a big deal. अभी हम जो भी प्रोजेक्ट हम तब्बा के साथ कर रहे हैं तो उसमें that's what we have to predict actual numbers. ठीक है. So that उस केस में when you predict numbers, so the numbers that are being predicted follow a probability density function. Any set of numbers follows a probability density function, and that is what the posterior is. If you are able to estimate the probability density function of the posterior, then that means that you are able to generate the predictions. बात खत्म हो गई. सही है?
जी सर.
हाँ, तो ये
तो
यही
सर
तो हमें
इससे MCMC से हम जो है वो क्लासिफिकेशन नहीं परफॉर्म कर सकते या सिर्फ रिग्रेशन ही कर सकते हैं. मतलब जैसे कि अगर मुझे सेंटिमेंट्स अगर मुझे वो करने हो मालूम सेंटिमेंट्स के ऊपर कि भाई अभी लेट्स सपोज अभी कोई सेंटिमेंट है और फिर उस सेंटिमेंट पे बेस्ड अगला सेंटिमेंट क्या होगा, तो
it is
उसके
possible
लिए
to
मैं ये
देखिए उसमें कुछ थोड़ा सा हमें चीजों को थोड़ा आगे पीछे करना पड़ेगा, लेकिन it is also possible to do that. हम क्लासिफिकेशन से भी डील कर सकते हैं because the class labels that you have given to the data also have a distribution. In that case, what happens is कि let's say I have this data, so I've divided that into, let's say this is the orange class and let's say I have this pink class. राइट. सो अब आप देखिए उसकी assumption क्या है. I assume that I assume that this part of the data follows some distribution. Let's say the normal distribution. Let's call it the normal distribution 1. It's a multivariate Gaussian, and I assume the same for this portion. So I assume the same for this portion as well. So, but I call this density multivariate Gaussian 2. So I can estimate these two separately. The class label does not have to come in the picture, right? समझ में आ रही बात की? मैं मेरा assumption class label देने का assumption आपका क्या होता है? Class label तो कोई भी class label is not part of operational data. I don't think so. It is ever part of the operational data. Class label is given by data scientists, right? So मेरा सवाल यही है कि आपका assumption क्या होता है class label देने में? I will just write that down. Your assumption in giving the class labels is that the rows of a given label are similar to each other. ठीक है? According to that label value. ऐसा ही है ना? For example, customers who defaulted and did not. ठीक है? The patterns of the defaulters is different from the patterns of the non-defaulters. So if O, let me say that this is P, okay, and defaulters is the O that जो आपको right diagram में नजर आ रहा है. So what do you mean by that? That means that the data for the defaulters follows another probability density function, and the data for the P follows another probability density function, and we can estimate both these functions separately. ठीक है? तो ये इस पे थोड़ा सा नेक्स्ट क्लास तक आपको वेट करना पड़ेगा कि क्लासिफिकेशन में एग्जैक्टली किस तरह यूज होगा, लेकिन मैंने आपको एक लॉजिकल एग्जांपल से ये बताने की कोशिश की है कि ये पॉसिबल है, क्योंकि if I am able to estimate the posterior of this multivariate Gaussian and the posterior for this multivariate Gaussian, then that means कि मेरा काम हो गया, खत्म होगी बात. If I have the posterior, then that means कि I know कि ये जो O क्लास के बंदे किस किस्म के हैं और P क्लास के बंदे किस किस्म के हैं, तो वो क्या वैल्यूज जनरेट करेंगे. ठीक है, क्लियर होगी बात?
यस सर.
हाँ, ये अभी
तो
आगे
मतलब कि हम हर
चलने
क्लास के लिए एक तरीके से वो जनरेट कर रहे हैं ना, हर क्लास के लिए हम लोग एक डिस्ट्रीब्यूशन की एस्टिमेशन कर रहे हैं.
जी, अभी जो मुझे लॉजिकली बात समझ में आ रही है वो यही है, बिकॉज मेरी assumption जो लेबल देने में वो यही है कि these two things are different from each other. तो in the stochastic domain that means कि they follow a separate Gaussian. बस, ठीक है? So using a set of probabilities for each room, ठीक है, these are actually the आपका जो prior है, यहाँ prior लिखना चाहिए. मैंने आपको बताया था कि for the MCMC methods we have to specify the prior and the likelihood function. वो आपके अपने experience पे होता है, statistical knowledge के base पे होता है, but it is possible to do that, right? So you specify the prior probabilities so that the search can start, so that the sampling can start. So you have to give the starting point that is randomly selected. To give it एक seed select करके randomly give it a value and it will start sampling from that value onwards. ठीक है? So you set the prior probabilities for each class and then you let the simulation to run, and then you will see that if you simulate yourself going from one room to another over a series of let's say 20 timestamps, and you simulate literally thousands of these simulations, then eventually you will converge to the true probability of being in each room. ठीक है, तो इसके सिमिलर चीजें मैं आपको नेक्स्ट टाइम इंशाल्लाह बताऊंगा, तो आपको जरा ज्यादा फायदा हो जाएगा. सो वी कैनॉट मॉडल रीजन, क्योंकि मैं t-2 पे देख नहीं सकता. However, by running the Markov chain for thousands of iterations, does give the long run prediction of what rooms you are likely to be in, because it is going to calculate your probability of being in each room if you run this simulation for thousands of iterations, given an initial value of the prior probabilities. That is the main thing that you want to keep in mind. ठीक है, तो अब आप ये सोचें कि it's not magic, right? I have a likelihood function and I have the prior function. I sample values from these functions and I estimate the posterior based on these values. And similarly, I can estimate the posterior thousands of times, and then obviously I can take the average, whatever जो भी था. ठीक है. So
प्रायर जो होगा वो completely randomly तो इनिशियलाइज नहीं करेंगे ना, हम एक सर्टेन बिलीफ के तहत उसको इनिशियलाइज करेंगे.
बिल्कुल, absolutely. The belief that we will have is the PDF of the prior. So we have to model that belief as a PDF in most cases. अभी मैं खुद इसका frankly hands on में देख रहा हूँ. अभी जो आज हम hands on देखेंगे उसमें तो we specify the PDF basically. PDF का मतलब ये होता है कि मुझे पता है कि जैसे एज का कॉलम है, ठीक है, एज का कॉलम मुझे पता है मिनिमम वैल्यू क्या है, मैक्सिमम वैल्यू क्या है, और मुझे आई नो फ्रॉम एक्सपीरियंस कि एज फॉलोज द गॉसियन डिस्ट्रीब्यूशन. सही है. सो आई हैव एन आइडिया ऑफ इट्स मीन एंड वेरिएंस. सो आई स्पेसिफाई दैट कि अकॉर्डिंग टू मी द प्रायर ऑफ द एज इज दिस नॉर्मल डिस्ट्रीब्यूशन. So in this way, given my knowledge, it is possible for me to estimate, give an idea about the prior of different columns and use that to estimate the posterior. ठीक है, तो उसमें you have to give me some time. मैं hands on पे जैसे हम आगे चलते जाएंगे तो आपको उससे इन चीजों की और clarity इंशाल्लाह आती जाएगी. So it does not matter where someone is in the house at one point in time. The point is that if you run the chain long enough, then you pass through each room long enough to understand कि इस रूम में मेरे होने का पैटर्न क्या है, जिसकी बेस पे जब आप एवरेज करेंगे तो you will be able to find out the probability of being in that room. इसकी मिसाल इस तरह दें कि आपका पूरा there's a pattern of you spending time at different places during the week. ठीक है. Now I want to estimate यार क्या probability है कि आप सब्जी की दुकान पे आलू ले रहे होंगे, क्या probability है कि आप चिकन की दुकान पे गोश्त ले रहे होंगे, क्या probability है कि आप यूनिवर्सिटी में पढ़ाई कर रहे होंगे, इसकी क्या probability है कि आप गाड़ी चला के पार्क जा रहे होंगे, ब्ला 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 ब्ला. ठीक है. अच्छा जी, किस तरह मालूम करें भाई? इस तरह मालूम करें कि भाई ऑब्जर्वेशन करें. प्रायर नॉलेज क्या है? प्रायर नॉलेज ये है कि जी जो हमारे नजर में जो प्रोबेबिलिटीज हैं वो ये प्रायर नॉलेज है कि इनका जो बाजार जाने का जो डेटा है वो नॉर्मल डिस्ट्रीब्यूशन को फॉलो करता है, और इनका जो मॉल जाने का डेटा है वो बीटा डिस्ट्रीब्यूशन को फॉलो करता है, क्योंकि हमें स्टैटिस्टिकल उसका नॉलेज है. तो आपने मुख्तलिफ जगहों पे जाने की डिस्ट्रीब्यूशन इनपुट पे कर दी. ठीक है. कुछ डेटा हमारे पास था, उससे हमने लाइक्लीहुड फंक्शन भी एस्टिमेट कर लिया. ठीक है. वो किस तरह होता है वो उसकी कैलकुलेशन आपको आराम से पाइथन के ऊपर कर सकते हैं यूजिंग द scipy लाइब्रेरी, बट उसकी मैं आपको मजीद हैंड्स ऑन पूरा एक मशीन लर्निंग का इंशाल्लाह करके दिखाऊंगा, फिर आपको मजीद क्लियर हो जाएगा. बहरहाल अब क्या होगा कि भाई सिमुलेशन स्टार्ट करो. चलो जी, सिमुलेट क्या हो रहा है कि जी मैं घर से निकला, रैंडम सिमुलेशन. मैं घर से निकला, मैं बाजार गया, सब्जी ली. दूसरी सिमुलेशन में मैं घर से निकला और मैं चिकन की दुकान पे गया, फिर मैं घर से निकला, फिर वहां गया. या फिर ये कि मैं एक जगह गया, उससे दूसरी जगह गया, उससे तीसरी जगह गया, उससे चौथी जगह गया. या एमसीएमसी की बात कर रहा हूँ. तो दूसरे इंस्टेंस में, दूसरी सैम्पलिंग में मैं घर से निकला, मैं तीसरी जगह गया, फिर दूसरी जगह गया, फिर चौथी जगह गया. तो क्योंकि मैंने आई हैव गिवन अ प्रोबेबिलिटी डेंसिटी फंक्शन ऑफ द लाइक्लीहुड and the PDF of the prior, so there are thousands of possible values कॉम्बिनेशन ऑफ लाइक्लीहुड एंड प्रायर्स, जिसकी बेस के ऊपर मैं पोस्टीरियर को एस्टिमेट कर सकता हूं, क्योंकि आई हैव गिवन यू द पीडीएफ, सो आई कैन सैंपल थाउजेंड्स ऑफ पॉसिबल वैल्यूज फ्रॉम ईच पीडीएफ एंड बेस्ड ऑन दीज टू वैल्यूज जो कि लाइक्लीहुड और प्रायर की आएंगी, आई कैन एस्टिमेट द पोस्टीरियर। सही है, तो वो किस तरह होता है वो आपको हैंड्स ऑन में मजीद क्लियर हो जाएगा। बट इफ आई रन द चेन फॉर थाउजेंड्स ऑफ आइटरेशंस, तो आई विल बी एबल टू कन्वर्ज ऑन द फैक्ट के my probability of being in the bazaar is this much, or being in the chicken shop is this much, or being on the road is this much, blah 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 blah. ठीक है, so I will be able to converge to the actual probabilities provided I run the chain long enough. That's what you need to keep in mind. ठीक है, okay, so this was the example of the average human height जो कि मैं compute करना चाह रहा था. So try to compute it directly rather than through prior and likelihood, which are both strange shapes. हाँ देखें, directly computation में भी you have to give it some knowledge of the likelihood and the prior. ऐसा नहीं है कि बिल्कुल ही आप खाली छोड़ देंगे, क्योंकि you have to give it a starting point, right? If I don't give it the likelihood and prior, it will never be able to estimate the posterior distribution. So in the library that we are using for hands-on, you have to specify these functions. You have to give it an idea कि मेरा distribution model क्या है. ठीक है, तो we will see how that happens. So draw samples from the posterior distribution directly and then compute the statistics like the average of the samples drawn, etc., etc. So that is the thing. The people who are doing Bayesian analysis, they integrate over the posteriors to make inference. ये main चीज है जो कि हमें याद रखनी है. ठीक है, if I am able to estimate the posterior value at each run of the MCMC, I am running the MCMC for thousands of iterations, so I have thousands of possible values, and then I can take the average of those values to find out the best posterior. ठीक है, वही वाला मिसाल है जो मोंटे कार्लो का है, बस इसमें सिर्फ फर्क ये है कि the sampling at time t depends on t-1. That's it. Monte Carlo does not work well in high dimensions, ये मैं आपको बता चुका हूँ, and assumes independence between samples. I have already told you this. Now in this case MCMC में the next sample is dependent only on the previous sample. Expectations are calculated along the way. That's the thing. And hope is, ये देखिए क्या लिखा हुआ है, ये मुझे बताएगा कोई लफ्ज क्यों लिखा हुआ है hope is?
सर बिकॉज़ कोई गारंटी नहीं है, मतलब हमारी उम्मीद ही है कि हो जाएगा, बट देयर आर सर्टेन टाइम्स व्हेन वी डोंट, आई एम अज्यूमिंग.
ये वी आर टॉकिंग अबाउट द बिलीफ. इट इज आवर बिलीफ बेसिकली. यहाँ पे बेसियन में हम वी आर टॉकिंग अबाउट आवर सर्टेनिटी और द बिलीफ इन द प्रेडिक्शंस दैट वी आर गेटिंग. So it's related to that basically. Hope is that with a large number of runs we can reach the goals. In fact, I have a strong belief and it turns into a certainty. देखें, यही तो बात है जो आप लोगों को समझनी है कि जब मैं सैम्पलिंग स्टार्ट करता हूं तो मुझे कोई सर्टेनिटी नहीं है. ठीक है, लेकिन जब मेरी सैम्पलिंग खत्म होती है तो मेरे पैरामीटर वैल्यूज कन्वर्ज कर चुके होते हैं एंड आई हैव सम स्टैटिस्टिक्स टू टेल मी कि एक्चुअल कन्वर्जेंस हो चुकी है. So now my belief, my doubt is converted to certainty that I have converged. I have converged. In the case of machine learning, there is no such guarantee that you have achieved the convergence. So आपने जो दिए थे, क्योंकि मशीन लर्निंग मॉडल सैंपल थोड़ी करता है. मशीन लर्निंग मॉडल जो आप पैरामीटर वैल्यूज देते हैं उस पे वो फिट करके निकाल के दिखा देता है. Even the grid search is not exactly the Bayesian thing that we are looking at right now. You sample directly from a probability distribution. That is not what machine learning is doing. So therefore, there is a difference between these two approaches. Barhal, although the first sample can be generated from the prior. अब ये देखिए ना क्या लिखा हुआ है कि you have to give the prior to kickstart the simulation. भाई आप कहाँ से उसको कुछ ना कुछ तो आपको prior knowledge देना पड़ेगा ना. So you have to give the prior knowledge to kickstart the simulation. लेकिन अब ये देखें आप, let's say you start the simulation from this point. So it is not magic, right? कि वो एकदम से सीख जाएगा. तो you have to give it some time कि भाई तुम ठीक है इस टाइम के अंदर, जैसे छोटा सा बच्चा होता है ना, जब when the kid is learning to walk, तो जो the mother holds the hand, ठीक है, the mother holds the hand for 1 week or 2 weeks or 3 weeks and then she just leaves it. Then what happens? The kid starts to walk by itself. The same concept is here. कि here the reason that we have to give the prior, ये orange ज़्यादा ही हो गया यार. The reason that we have to give the prior here is that we have to give some warm-up period. Like when you exercise, you warm up, right? So you have to give the algorithm some warm-up period. कि भाई तुम ठीक है अपना रास्ता तलाश कर लो. When you find out the way, then you can start walking yourself independently. ठीक है? So there is always a warm-up period over several timestamps or several hundreds of timestamps, in which the system is just finding its way based on the value of the prior and the likelihood that you are given. At one point of time, when the warm-up period is over, I will just write it down here so that it will be easy for you to remember. When the warm-up period is over, then the MC algo is able to sample directly from the posterior. क्यों जी ऐसा क्यों हो सकता है? Because it has learned somewhat the distribution of the posterior in the warm-up period. Like for example, when you go to you go to a new country, right? You go to Singapore for the first time, तो आप बाहर निकलेंगे एयरपोर्ट से तो आप कहेंगे यार ये कहाँ आ गया हूँ, क्या करना है, where is the hotel, where is my room, where do I have to go, how do the people look here, ठीक है, how do they behave, how much expensive it is, डबल रोटी कितने की मिलती है. There is so many uncertainties, right? But when you live there for like 2 weeks or 3 weeks, then you are over the game. You learn. Now you can generate your own posterior. अब आप सारे काम खुद कर सकते हैं. So that is the example जो कि ये है. And the mode of the posterior is called the map estimate, जो मैं आपको already बता चुका हूँ. हाँ, तो now please select this. हाँ, ये बस अब इसको देख लेते हैं. So अब हम इसको देखते हैं कि how does this work. Pick a random parameter value. So I'll just change the color here, just put it as green. So pick a random parameter value. Continue to generate the random values, which is the Monte Carlo part, but it is subjected to the rules for determining what makes a good parameter value. ध्यान रखिएगा बात की, बहुत critical बात है जो मैं आपसे कर रहा हूँ. So let's say I start the sampling from this point. I sample a value. ठीक है? If I'm doing MC, I sample a value. So I sample value from the multivariate Gaussian, for example. मुझे Gaussian की shape ही estimate करनी है. So I sample a value here. I should be able to understand कि which value is better. इसमें से कौन सी, is this a good value? So I'll just write it down here. So is this a good value? ठीक है? So I need some performance metric to determine that. Is this a good value or not? ठीक है? Then I sample the other value. Sorry about that. बहुत ही खराब हो गया. I sample another value based on this value. So I'll just put the arrow back. ठीक है? इस value से मैंने एक नया sample. Now ध्यान रखिएगा, that's how it proceeds. And let's say कि मेरा algorithm मुझे कहता है हाँ यार ये अच्छा estimate है तुम्हारा. Okay जी. From this I estimate this. Is this a good estimate? हाँ जी ये भी अच्छा estimate है. That's good. I'm making a progress, right? Is this a good estimate? Yes, this is also good estimate. So that's also good. So just I'll put the arrow back here. Is this a good estimate? नहीं यार, this is not a good estimate. So यार, let's delete this. ठीक है? So what about this one? What about this one? This one, everything is going like this. So अब होगा ये कि due to the evaluation that I'm doing at each step, I am able to discover this shape of the distribution. I gave you one simple simulation. ठीक है? Is this a good estimate? Yes. Is this one? Yes. Is this one? Yes. This one? Yes. This one? Yes. This one? No. This one? No. ठीक है? This one? Yes. This one? Yes. This one? Yes. This one? Yes. तो it is possible कि जो मेरा multivariate Gaussian है, it actually has this shape. It has this shape. It has this oval shape. So by sampling and evaluating at each timestamp, depending on the previous timestamp, obviously, I am able to approximate this shape because the samples are always going to revolve around in this circle. The sampling process is such that it is always going to revolve around in this circle, and this, students, is the shape of the posterior that I want to estimate. So अगर मेरे posterior की कुछ shape है given a multivariate Gaussian data, so MCMC method will definitely be able to sample enough to reach that shape जो कि मुझे दरकार है. ये बात समझ में आ रही है आप लोगों को? जी भाई, ये इसको समझ लीजिएगा, बाद में पछतावा होगा फिर. मैं बता रहा हूँ,
दोबारा से समझाए, मुझे नहीं समझ आई.
अच्छा,
The shape exactly.
देखिए, the PDF has a shape, right? ये तो पता है ना, every PDF has a shape. Every probability density function has a shape. So let's assume that I am estimating the posterior. So posterior has, let's say, this shape. This can only be the shape in the case of a multivariate problem, not a single variate problem. Okay? So in the multivariate problem, my posterior is following this shape. I want to estimate this PDF in order to generate my predictions. ये तो बात clear है ना आप लोगों को?
जी सर.
जी सर.
हाँ, ये चीज, that's the main point. अच्छा, now what happens is कि my claim is that I can use MCMC to estimate this shape. भाई कैसे होगी यार? मैं आपको I am giving you the likelihood and the prior. क्यों भाई, ये दोनों क्यों दे रहे हैं? शाबाश, जल्दी बताइएगा.
सर पोस्टीरियर कैलकुलेट करने के लिए चाहिए होता ना?
नहीं, एक और जवाब भी है इसका. कौन बताएगा? लाइक्लीहुड और प्रायर क्यों स्पेसिफाई किया जाता है? व्हाई?
Sir, to warm up the
Warm up.
MCMC.
That's the game. Primarily for the warm up period. You can use them later on as well, but primarily they are for the warm up period. ठीक है? अच्छा चलें, वो अब आप हैंड्स ऑन में देखेंगे ना तो वो आपको ज्यादा क्लियर हो जाएगा. अभी इसको रहने दें. वार्म अप बस कॉन्सेप्ट याद रखें. Let's say कि I randomly sample this point. The idea is, in order to estimate this oval shape, I have to sample points from the multivariate Gaussian based on the likelihood and prior. So I take one value from the likelihood function, I take one value from the prior function, and I sample this blue point that is shown. Depending on the distribution model जो मेरा है, वो आपको hands on में ज़्यादा clear हो जाएगा. ठीक है? So ये चीज क्लियर हो गई है. एक वैल्यू मैंने लाइक्लीहुड फंक्शन से उठाई, एक वैल्यू मैंने लेट से प्रायर से उठाई, उसकी बेस के ऊपर मैंने ये पॉइंट सैंपल कर लिया. नाउ आई एम यूजिंग MCMC. तो MCMC क्या कहता है यार? सबसे पहले तो आप इस पॉइंट को इवैल्यूएट करो कि इज दिस अ गुड एस्टिमेट. लेट्स अज्यूम आई हैव एन इवैल्यूएशन फंक्शन E. सो आई हैव एन इवैल्यूएशन फंक्शन E एंड E सेज कि हाँ यार, यू आर गुड टू गो. ठीक है जी. नेक्स्ट पॉइंट MCMC बोलता है आई हैव टू यूज द मार्कऑफ चेन. So based on the sampled value which is here, ये मार्कऑफ चेन अब बीच में ही आती है. ये जो सैंपल्ड वैल्यू आपके पास है, इसकी बेस के ऊपर दूसरी सैंपल वैल्यू निकाली जाती है. The second sample value is based on the first sample value. This does not happen in the Monte Carlo. You know it, right? Because they are independent samples. यहाँ पे वो मामला नहीं है. तो यहाँ जो वैल्यू आई है, that is arrived from the value here. ये चीज क्लियर है? इज दिस थिंग क्लियर?
जी सर.
हाँ ठीक है. अच्छा, अब आई आस्क की E सेज हाँ यार ठीक है. नाउ पुट द नेक्स्ट सैंपल. अब बिकॉज मैं रैंडम सैंपल जनरेट करूं, आई कैन गो इन एनी डायरेक्शन. क्योंकि मुझे तो सिर्फ आपने इन दो फंक्शंस में रेंज दे दिए, इनकी मिनिमम ये, इनका मैक्सिमम ये डिस्ट्रीब्यूशन फॉलो करते हैं, मेरी मर्जी में जो सा रूल्स है. अब लेट्स से क्या आई सैंपल एंड द सर्च गोज हियर. ठीक है? And then I said, is this a good point? So E says, absolutely not. This is not a good point. So I backtrack. ठीक है? Then I sample here. The next point, is this a good point? E says yes, it is a good point. Is this a good point? Yes. 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 In this way, वो search आपकी यूं करके चलती रहेगी. Are you understanding what I'm saying? The search will keep on occurring based on the value of the likelihood and prior that you have given, assuming that you have given the correct likelihood and the prior. This search will terminate in this shape. समझ में आ गई बात की? So I will just write that down so that it will be easy for you. Based on the likelihood and the prior that you have given, and assuming that these are correct, your MCMC search will definitely converge to the true shape of the posterior. And that means that it will be not biased, it will be consistent, and it is going to have the least variance, which is the requirement for the Monte Carlo thing. ये बात समझ में आ गई? Is this in clear?
सर क्लियर है. एक सवाल है, ये जो आपने जो एवेल्युएशन फंक्शन लिया है ई, और यहाँ भी जो मेंशन कर रहा है रूल्स फॉर डिटरमिनिंग व्हाट मेक्स अ गुड पैरामीटर, इट अज्यूम्स कि हमें पोस्टीरियर के बारे में कुछ पता है जिसकी वजह से हम उसको डिटरमिन कर सकते हैं ना, राइट? तो हम लाइक हाउ डज दैट वर्क?
That works in the same way. देखें Gibbs sampling जो है ना, Gibbs sampling. Now Gibbs sampling is one of the MCMC algorithms that we are using. तो ये तो मैं आपसे MCMC अप्रोच डिस्कस कर रहा हूं ना. अभी मैंने आपको एल्गोरिथम नहीं बताया कि एल्गोरिथम कौन सा है. The algorithm is going to specify this E. समझ में आ गई बात की? जो एल्गोरिथम हम यूज करेंगे गिब्स सैम्पलिंग में, फॉर एग्जांपल दिस E फंक्शन इज द कंडीशनल डिस्ट्रीब्यूशन कि probability of X given Y and probability of Y given X. In the case of Gibbs sampling, this E is the conditional distribution जो कि आपको दी हुई है. अब वो जब Gibbs आएगा तो उस वक्त हम बात करेंगे. But what I'm trying to say is कि कोई सा भी आप MCMC algorithm यूज करें, there are actually Metropolis, Hastings, we have Gibbs, and then we also have the nuts. I think nuts is based on this one. In fact, Metropolis, Hastings की बहुत सारी extensions बनी है, and sorry about that, one of them is nuts. So the algorithm will tell you कि E क्या है. ठीक है, समझ में आ गई बात की? आपका काम ये है कि you have to specify the likelihood, you have to specify the prior, and you have to specify the algorithm which is going to tell you the E, and it is 100% guaranteed that the search will terminate in the shape of the PDF.
सही है सर, थैंक यू.
That is the thing, ठीक है? So if a random parameter is better than the last one, it is added to the chain of parameter values. अब देखें ना, better कहाँ से पता चल रहा है भाई? ये E function है, ये algorithm का काम है कि वो बताए आपको, ठीक है? Then with a certain probability determine how much better it is, which is the Markov chain part. So that does it. So our best guess of the posterior. अब देखें ना, अब देखें यहाँ पे क्या हो रहा है. I started sampling from here. So this is the Markov chain which is increasing. So this is my best estimate of the posterior. This one. I assume, let's say I already know, given my likelihood and prior, that the posterior is supposed to have this shape. समझ में आ गई बात की? So I start sampling from here. The search proceeds in this direction. And then the search starts to go up like this. And then finally, the search starts to go up like this. So this histogram goes up and up and up and up and up until it fills up this area. समझ में आ गई बात की? You see, the histogram is nothing. The histogram is just sampling modeling the points जो कि sample हो रहे हैं. तो points की sampling की shape जो है वो distribution की तरफ जा रही है. That is what you need to understand. ठीक है? So MCMC estimates the posterior distribution of more than one parameter because MCMC works with multivariate data. उसका काम ही यही है, वो सिंगल वेरिएट के लिए तो वो होता ही नहीं है। फॉर n पैरामीटर्स देयर, अब देखें क्या लिखा हो, देयर एग्जिस्ट रीजन्स ऑफ हाई प्रोबेबिलिटी where certain sets of parameter values better explain the observed data. Ab here, this is not a region of high probability. Let me mark it here. For this data, for the given likelihood and prior, this is not a region of high probability. This is the region of high probability. Let me put that in another color. This is the region of higher probability, and this is the region of lower probability, the orange one. So the MCMC will 100% ensure through the evaluation function that all your points are sampled in the region of higher probability. बस ये main concept आपको याद रखना है, ठीक है? So it's something like this, कि you are just moving, it's always moving in this way. So you see कि this is the point which is rejected because it is not following the normal distribution or the distribution that you want to estimate, which is exactly the posterior. So अब देखिए ना, इसने सैम्पलिंग कहाँ से शुरू की थी? टेल के लेवल से शुरू की, but started the sampling went down up, but the sampling is going to remain in this area. That is what you need. इस area से बाहर कोई sample आया, it is going to be rejected because this area forms the crux of the normal distribution of the posterior that we want to estimate. So the MCMC will ensure that this happens. ठीक है, सही है? हाँ जी, हाँ ठीक है, ठीक है।
अच्छा, ये तो न्यूरल नेटवर्क जैसा है।
किस तरह है भाई? न्यूरल नेटवर्क का कहाँ से हो गया भाई? क्या है? तभी सही है।
न्यूरल नेटवर्क की ट्रेनिंग,
आपने
ट्रेनिंग मैकेनिज्म जो है, जैसे इवैल्यूएशन का फंक्शन है, एरर, फिर उससे पता चलता है कि नहीं वो वाला चीज मतलब उस डायरेक्शन में नहीं जाने का।
हाँ, मैं समझा कि आप एल्गोरिथम के हिसाब से कंपेयर करें, लेकिन
न्यूरल नेटवर्क उस हिसाब से नहीं।
न्यूरल नेटवर्क लर्न्स अ नॉन लीनियर मैपिंग फ्रॉम द इनपुट टू द आउटपुट। न्यूरल नेटवर्क का काम ये, व्हाई इट इज नॉन लीनियर? बिकॉज you use the activation functions. And why do you want to make it non-linear? So that we can do the gradient descent on the cost function. और इसकी कोई reason है ही नहीं, ठीक है? तो अब in that case I'm not sampling. That's a completely different process. I'm trying to discover कि मेरी non-linear mapping कौन सी है जो input से मुझे output generate करके दे देगी. That's what I want to discover, right? And it is such a complicated function that no one can write that function जो कि neural network learn करता है, because it is based on thousands of weights, hundreds of weights. How can you write the function? You cannot write the function. It's not linear regression. So it is not sampling, it is estimating the function which is mapping the input to the output. So algorithmically there is no comparison. Although जो आप बात करें वो अपनी जगह पे बिल्कुल सही है कि हमारे नजर में the MCMC algorithms and the traditional machine learning algorithms, हमें तो अब इनका आपस में मुकाबला करा के देखना है. There are also other Bayesian approaches जो कि आपने इस कोर्स में भी पढ़नी है. अब हमने बेसिकली इनका आपस में मुकाबला करा के देखना है कि किस किस्म के डेटा सेट्स के ऊपर ये अप्रोचेस जरा ज्यादा अच्छी चलेंगी. ये मसला है इस वक्त, क्योंकि अभी हमारे इवन इन द डीप लर्निंग रिसर्च सिनेरियो the Bayesian sampling approaches are getting a lot of success. I mean, they are helping deep learning to converge faster. That's a big deal. The sampling approaches, ठीक है? तो इस वजह से मुझे इस चीज में बहुत कंसर्न है, and I do want to get this investigated. That's the thing, ठीक है? So अब बस ये, इसके बाद हम hands on, बस ये आखिरी स्लाइड है. So the algorithms, कौन से भाई algorithms को नाम बताएगा मुझे? Gibbs है, और क्या है?
Sir, Hastings.
हाँ, Metropolis, Hastings, Gibbs, Nuts, etc. ठीक है? So they are only defining the different ways of constructing the Markov chain when performing each Monte Carlo sample. That means primarily the evaluation function and generating the chain. Okay? They are sensitive to their starting point, so you have to understand that we do need a very good starting point. We do need the likelihood and the prior. That is the reason we give the likelihood and the prior, so that we can have a very good start. in the warm up period, often requires a warm up phase or a burn in phase, दोनों नाम सही हैं, to move in towards a fruitful part of the search space, after which the prior samples can be discarded and useful samples can be collected. ठीक है, ये मैं आपको समझा चुका हूँ. This is an example of a random walk. A random walk means that the next sample comes randomly based on the previous sample, so there is no evaluation function. So if there is no evaluation function, then this becomes a random walk. So random walk typically is served as the baseline. सही है, समझ में आ गई बात की? Random walk जो है वो primarily can be termed as the baseline for your own MCMC algorithms or your own, आपका अपना एल्गोरिथम अगर है तो आप उस पे उसको कर सकते हैं. अच्छा, अब इसको छोड़ दें. Let me just yeah, so I hope that you can see this. So it's been a very tough ride. So let me just clear all the outputs here. So I will just show you one thing. The basic library for the क्या हो गया यार? Sorry about that. So the basic library for doing this Bayesian inference is Stan. ठीक है, जो कि basically it has two main implementations. One of them in R and the other one very recently in Python. So R का जो है वो भी मैं आपको दिखा देता हूँ. So you can, if someone wants to work in R, I have absolutely no issues. You can work on R. So that's called R Stan. ठीक है. And if you want to work in Python, तो क्या यार?
Pystan.
So this is RStan. RStan is that you just download R Studio. अब तो R उन्होंने बहुत आसान कर दिया with the R Studio. बिल्कुल बच्चों वाली चीज है. तो इस केस में जो है वो अच्छा, it's here. So the basic library is here, but उसके बाद आप जो है ना वो Python version is Pystan. So Pystan on Windows, Stan, Pystan, whatever. So this is Pystan. So you can see कि दोनों का तकरीबन same ही है, लेकिन Pystan is still under development. ये अभी बहुत सारी चीजें इसके भी formalize हो रही हैं. On the contrary, RStan is completely available. It has many functions. So if any one of you wants to do the project on RStan, I have absolutely no issues. We are just looking for the predictions that we want to generate. ठीक है. अच्छा, अब प्रॉब्लम ये है कि Pystan में I had to spend a lot of time yesterday on this. The default compiler, for example, if you go here, yeah, so you write Python. So it is using this Microsoft compiler version 191664-bit. सही है. So the Python sorry about that. So the Pystan is not going to accept this. ठीक है. Pystan जो है वो it is not going to accept this compiler. So ये कल मेरा बड़ा time लग गया था इसके ऊपर, क्योंकि I will also show you this के this is WinBuilds. WinBuilds is actually the not this one, sorry about that. ये था there was मैं भी भूल गया उसका नाम क्या था यार. I just forgot. Just let me check here. That might come in handy for you later on. हाँ, maybe इसमें होगा वो. हाँ, तो ये Visual Studio add-ons का कोई था मेरे ख्याल में कि it's very strange. It's not coming. But it allows you to install different types of compilers but I tried them out, but none of them were working. So then I found out that I have to install this compiler, which is given on this link. So we'll just go here. So oh, sorry about that, it's not being copied. Yeah. ये अभी आ नहीं रहा है for some reason. यार क्या है? अच्छा, Pystan, let me just go through. This is, I'll just share this with you again. Where is this? Yeah. So this is the link, you can follow it. So यहाँ मुझे बड़ी मुश्किलों से पता चला कि it is not supported. Prerequisites. Latest Windows.html. Just wait up. ये देखें, Pystan on Windows. Pystan is partially supported under Windows with the following caveats. MSVC compiler is not supported. ठीक है? So ये चीज बड़ी मुश्किलों से मुझे समझ में आई. तो we need to install this compiler, which is being W64 compiler. So ये installation का मैंने आपको तरीका जो है, I have written it down here. So let's so you can follow the instructions here. So let me just go back to there. So ये सारी instructions आपने Anaconda की prompt पे लिखनी है, जो मैंने अभी आपको prompt दिखाया था ना, conda info, conda update, conda create -n, this. अब just put the version that जो आपका है, activate this. ये तो खैर okay. This is if you want to create a separate environment, you can create. मैंने नहीं create की बहरहाल. This is the command that you want to put. मेरा कुछ एक दो errors भी आए थे. I think there was some connection error, so you will have to ensure that this finishes up. You will not need to do this one, build compiler being. इस step की जरूरत नहीं, क्योंकि automatically ये आपकी जो CFG file है ये configure हो जाएगी. तो both of these steps, you will not need these two steps if you have the latest version of Python, because this will be updated automatically. ठीक है? Yeah, so you will have to install Python. Python का मतलब है कि Python executes the C code within the Python. ठीक है? That's called Python. तो you can write C code और Python उसको execute कर देगा as it is using the C compiler जो कि आपने install किया है. ये तो already आपका installed होगी, blah blah blah. फिर आप उसके बाद Pystan install करें. So just follow the instructions which are here. उसमें errors वगैरह आ सकते हैं, तो वो किसी और से पूछ लीजिएगा, मेरे पास टाइम नहीं होगा आपको हेल्प करने का. पहले मैं अपने आप गया था, फिर मैं टाइम नहीं दे पाता हूँ बहरहाल. So let's go through this के yeah, so Pystan is Python's implementation of the Stan language for MC modeling specifically. Stan generates MC sample using Hamiltonian Monte Carlo, which builds upon the Metropolis Hastings. That's what I told you. By incorporating many theoretical ideas from physics. Actually, by default, it implements a version of HMC called the no U-turn sampler, nuts. Okay. So this is the sampler which is being used in the current version of Pystan. So now determining the bias of a coin from observed coin tosses. So I'm going to apply here. Should we take a break?
Yes, sir.
10 minute break ले लें?
Yes, sir.
जी sir.
Yes. So our first problem is that we want to determine the bias of a coin from the observed coin tosses. So it's a pretty simple problem. और इसमें जो the intention is actually to like we are going to give the algorithm some data, right? कि हम कहेंगे उसको कि for example, if I sample the coin 100 times or if I toss a coin 100 times, then at least 60% of the time वो heads आना चाहिए. So yeah, so if by tossing this and sampling it again and again, I am able to achieve a frequency, the probability of heads as close to 60%, then that means कि I'm on the right track. The coin is not biased. तो मैंने जो उसको starting point दिया था, it's going to converge around that. ठीक है, so then that means it is not biased. So let's see how that works. ठीक है, तो let's assume कि we will have a beta distribution as the prior. ठीक है, we have not gone through the beta distribution, but I'll tell you right now that beta is a family of continuous PDFs, which is defined in the interval 0-1. So that is why a coin toss के लिए हम beta distribution ले रहे हैं, which has two parameters, alpha and beta. So normal distribution also has parameters. So beta distribution has two parameters, alpha and beta, that appear as exponents of the random variable and control the shape of the distribution. So if you execute this, so you can see that for this I took from Wikipedia, for different values of alpha and beta, you are able to get different shapes of the beta distribution. There's a probability distribution. I don't think it's normalized. I think probability is here on the x-axis. So no, so this one of them is alpha, the other one is beta. So this is how the shape of the distribution is changing. So it's not always normal. You can see it can have different shapes, but the main point is that it is sampled in the interval 0-1. That is the main point. It's always sampled in this interval, which is between 0 and 1. Okay? So how do we use that? So let's start now. Just to tell you how does the beta distribution work. तो ये अलग से मैं आपको ये डाला है कि just import this beta. This is just the configuration for that. So let's have the value of 2.31 for alpha and 0.627 for beta, and I can just print out these values by calling the beta.stats based on this. So I think MVSK is the, मैं इसका मतलब भूल गया यार MVSK का, the moment. So this is pretty simple one, just and you can plot the beta one. So this is the distribution for this given value of alpha and beta. So just plotted that. Okay, so just to show you how it works. And so this is for the prior. So we are assuming that the prior distribution of the coin toss follows this. So yeah. So कोई बता सकते हैं इसका क्या मतलब है? Hey. So this is the shape of how the probability is varying. So as we increase the value here, this value as we increase here. So as we increase the value of x, but the point is that this is the probability, right? The probability यहाँ vary कर रही है based on this one variable, which is the one variable. अच्छा ये जो variable है, this variable is calculated based on the value of alpha and beta. So as this variable increases, the probability converges towards 1. So that's how it is in this case. ये हमारा problem नहीं है. And we assume that the binomial distribution is the PDF for the likelihood function. So binomial distribution क्या होती है कि it assumes in which we have two possible outcomes. In that case, we are using a binomial. So it's a discrete probability density. Beta is in fact continuous, and binomial is the discrete one, in which the number of successes in a sequence of n independent experiments, each asking a yes/no question, and each with its own Boolean valued outcome, success or failure. So I have a sequence of experiments, and in each experiment I have a probability of success P and a probability of failure 1 minus P. Okay, and I'm putting that in a sequence, so I can model the formula. So iska bhi ek formula hai beta ka aur iska bhi formula hai, but that's not important right now. I'm just giving you examples ke it has two parameters N and P, and beta has two parameters alpha and beta. Okay, so you can just plot it here. So is a discrete one, so it can take 5 different values based on these values. So obviously N is 5. So 5 different values may the probability is distributed in this fashion. It's a PDF. Okay, so now back to the original question. ये जो scipy.stats के अंदर all the probability density functions are there, in fact, so you can try them out yourself. Import binomial, import Gaussian, import whatever. So आप try करके देख सकते हैं. जब हमारे पास actually training data आएगा, then we will need to really understand what is going on, because we have to give my guess is that we have to give the priors and the likelihood functions. ठीक है, बहरहाल. So now we are on to this. The problem that we are solving, so we don't need these, but still they are given. Import Pystan, blah 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 blah. Precision is 4. Style the plot, ggplot, blah blah blah. अच्छा ये 2 दफा कर दिया. Sorry about that. This one we did twice. So you just import this. Okay, अब Stan जो है, you need to keep in mind that it has basically 3 parameters that you have to specify. One is called the data block. Data block के अंदर you specify the data that will be sampled. ठीक है? तो coin toss के चक्कर में this is the model, in fact, जो कि आप Stan block में पहले डालते हैं. This model seems quoted to me, but this is actually the C code that will be executed by the C compiler that you just installed. So in this case, we have 2 variables that we are using in the sampling process. One is the number of heads, क्योंकि हम bias निकाल रहे हैं इसमें ना, तो हम उसको number of heads का एक initial guess देंगे कि I'm guessing that out of 100 tosses, 61 should be heads, or 60 should be heads, or 61 should be heads. So we want to see whether the MCMC process is going to converge to that. So let's see how that happens. So Baral, I have these 2. I will be tossing the coin a certain number of times, and I will be actually measuring the number of heads that are coming. So these are two variables. So these go inside the data block. The types and dimension of the data. So type bhi hum mention kar diye. Lower means the lower bound. So minimum value is 0. Okay, that's what it means. This is an optional thing. You can tell how you want this data to be transformed in this function, but that is a complicated thing right now for us. So we will leave them as it is, these 3 functions. Okay. The second block is the parameter block. It specifies the parameters. So in our case, the parameters are just P, which is the probability of measuring a head. So where the lower value is 0 and the upper value is 1, obviously. Okay. And then I have to specify the third, which is the model or the distribution. It goes in the model block. So अब आप देखें कि distribution में क्या बता रहा हूँ कि P, the parameter P follows the beta distribution because I'm sampling it between 0 and 1. So the number of heads that comes up should follow the normal distribution, beta distribution. And the parameter Y, it follows the binomial distribution. So in our case, P is the prior information that I'm giving. सही है? And Y is the likelihood function that I'm interested in. Okay? So the P is the prior information about P. Okay, on the prior, I assume that P follows the beta distribution 2,2. ये prior का मेरे पास है. आपको याद है जब हमने शुरू में वो 3 curves देखे थे? One of them was the prior, other one them was likelihood, and the third one was the posterior. So that's what we're doing right now. We say that based on prior knowledge, I believe that P, the number of heads, follows this distribution. and y is actually the binomial distribution जो कि actually हमें coin toss से मिलेगी, which is the likelihood, and now we have to approximate the posterior. सही है? So that's the scenario here that we want. Again, I told you that these three functions are optional functions right now for us. Maybe for the projects you will need to use them. Then you specify the data. So I'm going to sample it 100 times. Okay, I will have 100 iterations of the chain. No, sorry, not the 100 iterations. So को बता सकते हैं n क्या है? Number of tosses is 100. So in each iteration, I'm going to toss the coin 100 times. ठीक है? Is this thing clear?
सर iterations 1000 है और हर iteration के अंदर 100 tosses हैं.
हाँ, तो that's what happens in Monte Carlo, right? Monte Carlo में हम यही करते हैं ना कि हर iteration में हम ढेर सारी चीजें sample करते हैं और उनका फिर average ले लेते हैं बाद में. So in one sample, I have to sample many things, and I do the sample also thousands of times. ठीक है? So in each sample, I'm going to sample 100. I'm going to toss the coin 100 times. And let's assume, अब देखिए ना, ये मैं उसको क्या कह रहा हूँ, y61, ये मैं उसको डेटा दे रहा हूँ. This also acts as my prior knowledge. सही है कि मेरे prior knowledge के मुताबिक this is what it should be. अब होगा क्या? I have nothing to do with this. This is just a kickstart. ये मेरा prior knowledge है कि अगर मैं 100 दफा coin निकालूं तो कम से कम 61 दफा उसमें क्या आना चाहिए? Heads आने चाहिए. ये मेरा prior knowledge है. And that is what I want to check. कि if you sample it, if you toss, if you simulate the sampling of a coin thousands of times, and in each simulation you are tossing the coin 100 times. So does my probability of getting the head P converge to 0.61 or not? सही है? समझ में आ गई इस बात की? So what to investigate? I have prior knowledge that my coin is going to give 61. Yeah, that typically the 50 paisa coin should give 61 heads out of 100 tosses. ये मेरा prior knowledge है, ठीक है? And I believe in that knowledge as firmly as possible, ठीक है? So now I want to investigate whether a given coin or whether a given 50 paisa coin is biased or not. समझ में आ रही बात की? So I simulate MCMC. So in MCMC, in each iteration, I do 100 tosses, record the number of heads. Again, 100 tosses, number of heads, 100 tosses, number of heads, 100 tosses, number of heads, and then I put the average. ठीक है? So it seems like Monte Carlo, but actually it is Markov chain Monte Carlo. अब वो जब हम nuts algorithm को देखेंगे, पता नहीं उसको, I don't know कि उसकी अभी तफसील हमें देखने का time मिलेगा कि नहीं, but it follows some algorithm. ठीक है? So I hope that this is clear. So now when I execute the model, so in the model also you need to understand this. Yeah, so iter refers to the total number of samples that will be generated. ये आपको समझ. Chains is the number of chains from which samples will be combined. So I can have multiple chains. In this file, currently I just have taken one chain. So एक ही chain में तुम सारे करो, लेकिन I can take multiple chains and also put the average over the chains. Is the number of chains from which samples will be combined to form the posterior distribution. तो ये मेरे पास एक option है. Chains को बढ़ा भी सकते हैं in order to really ensure yourself के the result is absolutely on spot. ठीक है? Because the underlying Markov process is stochastic, it's advantageous to have more chains. That ये देखिए ना, that will initialize at different locations in the parameter space, but they will always converge on the same location. So one chain will start from here, and do this, and end here. The other chain will start from here, do this, and also end here. Third chain will start from here, do this, and also end here. So जितनी ज़्यादा chains ले लेंगे उतना हमारे लिए beneficial होगा result पे वो करना. लेकिन फिलहाल हम अभी एक ही chain ले रहे हैं क्योंकि ये एक expensive procedure होता है. Warm up is also called the burn-in. You do understand what this happens, right? So by default, this is half of the iteration. So if you specify 1000 iterations, that means 500 is going to be the burn-in time. ठीक है? With 4 chains, we will have 2000 samples in total. और ये चीज बड़ी जरूरी है, आखिरी चीज है कि thin specifies an interval in sampling at which samples are retained. सही है? So if thin is equal to 3, every third sample is retained and the rest are discarded. Because you know, आप यहाँ से start कर रहे हैं, sample, like this. So maybe you say ये ठीक है, अगला कहते हैं यहाँ पहुंच जाओ, आप इसको डिस्कार्ड कर देते हैं, आप कहते हैं दोबारा सैंपल करो. just because things are going randomly, so you really want to be sure that I want to go down, so sample it again, just ignore the third one, sample it again and take that as the third one. So that is called the thinning factor. सही है? So ये सारी चीजें यहाँ आपकी स्पेसिफाइड हैं. थिन तो मैंने अभी डाला नहीं है इसके अंदर, नीचे कहीं होगा उसके अंदर ना थिन का जो भी मामला है, अभी यहाँ पे वो है नहीं, थिन है नहीं यहाँ पे. बहरहाल, so let's execute this. So you see deprecation warning, blah blah blah, compiling the C++ code for model this. इसको थोड़ा सा टाइम लगता है एग्जीक्यूट होने में, so let's wait up for that. Recording progress, yeah, sorry, so we missed this recording, guys. So I explained all these things, that this LP is actually the log posterior. So we want to check that for convergence, and basically this is the posterior distribution that has been estimated, which is normal distribution with a mean of 0.61 at the 50% level, which is also replicated here. So LP is just meant to check. So we saw, okay, we can put that as a data frame, or we can extract the keys and then plot it. So the average behavior is the normal distribution here. In this case, we're looking at the problem of estimating the mean and standard deviation of a normal distribution through MCMC sampling. So what we're doing here is that we have the model which follows the normal distribution. I'm going to give you different values of mu and sigma based on these two ranges, which I told you that we always give. So we're going to be sampling from different values of mu and sigma based on these ranges which have been given to us, and we are going to put the values in this formula to get the value of y. And the data that we are going to be concerned is the number of samples in each iteration that we're doing, and the actual y value that we are getting. So we are interested in getting the y value. So I get the so this will take some time again. So we are interested in getting the values of mu and sigma. So we want to understand what are the ideal values of mu and sigma to which the MCMC algorithm will converge. We have given it's a particular range जो हमने दे दी है, and the distribution that we expect to follow is this distribution. So I provide this data. I provide data कि आपने a number of terms in each iteration you have to basically sample 100 times the normal from the normal distribution given these ranges, and the y value you are going to get from this np.random.normal. तो अब आप इस बात को समझने की कोशिश करें कि मैं 100 दफा सैंपल कर रहा हूं एक आइटरेशन के अंदर, और हर सैंपल में मैं y की वैल्यू आपको बता रहा हूं which is coming from a normal distribution. So I have the value of y already, and based on the value of y in each sample, I have to estimate the ideal values of mu and sigma to which the MCMC algorithm will converge. So जब भी मेरे पास sample होगा, I already have the value of y with me because I am sampling that from this. So this is can be considered my prior knowledge. ये भी मेरा prior knowledge है, ठीक है? So the data that you specify here, you have to specify the starting point for that. So this is the reason कि मुझे warm up के लिए चीजें बतानी पड़ती हैं. बहरहाल ये अब हो गया है. Now I can fit it. So you can see कि given your data here 0 to 100 and 0 to 10 for the sigma, the ideal values of mu and sigma are 2.03, which is the at the 50% level, and you can see कि LP is 1, so it has converged. Mu is 1.02, is very close to 1, so these values are converged in fact. So इसको अगर हम बनाएं, this is the shape you see कि ये MCMC को दिखा रहा है वो. How does it, देख रहे हैं आप क्या हो रहा है, ये समझ में आ रही है? This is for mu and this is for sigma. So the distribution of mu and sigma which has been sampled based on this method is actually following the normal distribution. So that is how the MCMC algorithm is proceeding, पहले यहाँ फिर यहाँ exactly. So that is what happened over so many iterations. ठीक है, clear हुई बात?
Yes sir.
So maximum जो आपने निकालना है अगर finding the maximum posteriori, it's not a problem. You already have the normal code. This the problem above, आप उसको दें and just call sm.optimizing and then print the op. So it's going to give you the maximum value of the posterior function. So I'll just wait for it to execute. I mean, the values at which the posterior function has the highest probability. The values at which the posterior function has the highest probability. So just wait up for that. Okay, so I'll just repeat that because I forgot. So we can reuse a fitted object. Okay, if we finish the chain at one point, I can specify new data and I can start the chain again from that point onwards. So that fits it here. I can save a model or I can load a model. So for that, I have to definitely specify this byte array because it does not by default accept the byte stream. So I have to put the B here. That's why I put the B. Yeah, so this I already did. The model is saved. The model can be loaded. Yeah, so the model is loaded here. So this is the model. And you can see कि पहले जब हमने किया था तो 111 था, 1.01 आ रहा है. So I mean that's because of the sampling thing. Now something important which is estimating the parameters of a linear regression model. So y approximately equals to ax plus b as we know, but let us assume we want to reformulate this equation. E is the error term here, which is the default inclusion in the regression equation. We want to reformulate this to sample from a probability distribution such that y is approximated by a normal distribution in which mean is ax plus b, and the standard deviation is sigma multiplied by sigma. Okay, so sigma is the sigma squared, basically is the standard deviation. अब मुझे a और b की वैल्यू एस्टिमेट करनी है using linear regression, but I don't want to follow the normal linear regression. I want to use that using MCMC sampling. तो अब क्या है कि मैंने a और b के priors कुछ बताए कि we believe कि a follows the normal distribution with a mean of 0 and a variance of 100. Ditto for b, and we believe कि sigma follows a uniform distribution sampled between 0 and 20. बस ये ठीक है, ये मैंने अपना बिलीफ बता दिया, प्रायर बिलीफ. These are the three parameters I want to estimate. In this case, I do specify the transform parameters. Let me just the transform data. So I have n, x, and y. I have a, b, sigma, and I transformed it because I have to use a, b, sigma in this equation. So mu I equals to axi plus b. where xi means the basically x value, mx plus c. So a is equal to m and b is the constant. In the model, the sigma follows the uniform distribution and y follows the normal based on mu and sigma. Sorry for that. Just so, बस ये आखिरी example है for today. I have to estimate the values of these three parameters through the MCMC. So whatever parameter you want to estimate, यानी जिनका posterior आपको calculate करना है, so just say A, B, sigma. ठीक है, वो you have to write them here. And if you want to use them in some other equation, then you use that using transform parameters. For example, I create this parameter mu, which is not mu like mu, which is not the mean in fact. Mu is just a term for y equals to mx plus c. So mu I equals to axi plus b. Okay? And the model is that sigma follows the uniform distribution and the y follows the normal distribution based on mu and sigma. सही है? तो mu ये वाली चीज है जिसके अंदर a b दोनों आ रहे हैं और sigma जो है वो आपको यहाँ से मिल जाएगा. So mu की वैल्यू आपको कहाँ से मिलेगी? A and B की सैंपल से, और sigma की वैल्यू आपको कहाँ से मिलेगी? वो आपको यहाँ से मिलेगी. सही है? So n क्या है? I have to specify these values. N is the number of times you are sampling once in each iteration. A is 6, B is 2. And then I'm just putting that in equal intervals, and I say कि y equals to this. ये मैंने initial उसको data दिया है, ठीक है? And the linear regression data is nxy, n equals to n, x equals to x, y equals to y, where the values are coming from here. And then I say fit the model change equals to 1, blah blah blah. So model, I mean, you first have to determine के parameters क्या हैं, and write down the transformations if you want. Then you have to determine कि data कौन सा है जिसकी base पे सारी sampling होगी. So I'm going to sample n, x and y. Based on n, x and y in the sample, I'm going to estimate a, b and sigma. That's it. Okay. So if I just fit the model here, this is going to take some time. So by sampling different values of n, x and y, I'm going to estimate the values of a, b and sigma at each iteration and each go of each iteration. So I'm going to estimate the values of a, b and sigma, और मैं ये देखूंगा कि वो कहाँ पे जाके converge करते हैं, ठीक है? तो अगर आप इनको run करें, so you can see कि a is 7.39, this is this. mu1 इसलिए उसने बताया है क्योंकि I have created that as a transformed parameter. कि mu1 is dependent on ax and b. So I get the value of ax and b from here. तो जो भी x था उसकी base पे मैंने mu1 निकाला. Why it is going up to 11? Because I specify in each iteration you have to sample 11 times. So mu1 will be estimated 11 times. So you can see that this is the result over thousands of iterations. कि जो y की value आ रही है वो ये आ रही है. mu1 is this one, the second time is this one, third time is this one, etc. So अगर आप इसको plot करें, so a b sigma तो इसमें नहीं आया, a b का है. So just let me put the sigma as well. A, B and sigma. So sigma, because sampled from a uniform distribution, so it's a different shape. So अब आप देख रहे हैं कि can you see the search space? Can you see the sample value? The sample value is remaining in a particular range. That's what is more important. That's the thing. The sample value is moving around in a particular search space. It's not going like this. तो मैंने आपको random walk दिखाई थी अभी. I showed you the random walk, right? Look at this. Is this moving in a particular search space? Absolutely not. So yeah, so on the contrary, when you see that, you can see that it is moving in a particular search space. So that finishes it up for today. So what we have to now understand is that I got different machine learning algorithms, right? अब now I have to go with more complicated data sets जिसमें मैं अभी तो मैंने आपको गिब्स भी नहीं पढ़ाया क्योंकि अब टाइम इज आई थिंक 11:30 हो गए. We'll do that next Monday इंशाल्लाह. गिब्स सैम्पलिंग, मेट्रोपोलिस, हेस्टिंग्स और ये जो भी नट्स वर्ड्स हैं जो भी हैं उसको हम देख के we're gonna do more aggressive hands on इंशाल्लाह, in which we will have real data sets जिसमें हम ये चीजें जरा thoroughly apply करके देखेंगे कि what's happening actually. So obviously you do understand कि when I sample from large data set, so the sampling will take some time. Our sampling has its own parameters as well, लेकिन उसके साथ हमें गुजारा करना है. तो अब यही चीज देखनी है कि जो अब देखें ना, the posterior distribution, मैं कहता हूँ posterior, if I want to predict A, I got the posterior. मुझे उसकी पूरी probability density मालूम है, तो मैं जो चाहे इसको सैंपल, जब मुझे probability density function आ गया तो भाई मैं उससे अपनी डेंसिटी कर्व निकाल के मैं जो वैल्यू निकालना चाहूँ मैं निकाल लूँ. उससे मीन वैल्यू बता दूं कि मीन वैल्यू प्रेडिक्शन की 7.39 है. तो दैट्स द थिंग कि मैं सैम्पलिंग से मैं प्रेडिक्शन जनरेट कर रहा हूँ. दैट्स द थिंग दैट वी वांट टू वर्क विद इन द रियल डेटा सेट्स. ठीक है, ठीक है. और कोई भाई क्वेरीज तो नहीं है? इज दिस ओके? कुछ समझ में आया लोगों को?
यस सर.
So you do give it a shot. मैं ये obviously मैं अभी सारी नेट की examples ले रहा हूँ, but I have not discovered very concrete examples as yet in Pystan. I think कि हमें शायद R पे shift करना पड़े अगर वहाँ पे samples हो, because I don't want to waste time in converting R code to Python code. We just want to understand how this works, right? तो R में code लिख लें, उससे क्या फर्क पड़ता है? But I will try to still do that in Python first. बहरहाल तो लॉजिस्टिक मॉडल है, इस तरह दूसरे रिग्रेशन मॉडल्स हैं, तो हर एक का हमें करके देखना है कि होता क्या है. सही है, ठीक है. तो आपका होमवर्क ये है कि आप इसको थोड़ा सा खुद चला के देखें, ट्राई आउट डिफरेंट एक्सपेरिमेंट्स. अभी मैं कोई असाइनमेंट नहीं दे रहा, लेकिन जस्ट ट्राई इट आउट एंड सी व्हाट्स हैपनिंग. सो अब अभी हमें अच्छी तरह पता चल गया है कि वी कैन एस्टिमेट प्रेडिक्शंस based on sampling. We just need to know the prior information and we just need to know कि वो distribution कौन सी follow कर रहे हैं. सही है?
सही है सर, थैंक यू.
चले सही है फिर. ओके, नेक्स्ट वीक मिलते हैं इंशाल्लाह फिर. सही है?
सर अल्लाह हाफिज़.
अल्लाह हाफिज़.